This will be our fourth video on basics of quantum mechanics for AP Physics 2, and I'm just gonna wrap up some problems, practice questions for you, hopefully another 30-minute video. And if you have more questions in the future about this topic, or you find questions you didn't know how to solve, just message me, email me, and I will figure them out for you. Let's jump to the practice. So in this question, they say two metals labeled S and T are used in separate photoelectric effect experiments. S has a smaller work function than T. Which graph best represents the electron energy versus frequency plots for the two experiments? Because S has a smaller work function, I know that S will have, so the work function, right? It's the energy that is coming from the photon, that like the minimum energy coming from the photon just to rip off the electrons, and that is equal to h times the frequency. So it has smaller cut-off frequency as well. So S has smaller cut-off frequency. So I see this one has smaller cut-off frequency. This wouldn't be my choice. This one has smaller cut-off frequency, and this one would have negative cut-off frequency. So this cannot happen. So this cannot happen, and you cannot have zero energy needed to cut off the electrons from the surface. So the answer would be on E. In this question, they say an electron with initial kinetic energy E is accelerated so that its kinetic energy is doubled. If its original de Broglie wavelength was X, its de Broglie wavelength after the energy increase is... So de Broglie wavelength has a formula where we have the lambda, the wavelength, is equal to the Planck's constant over the momentum of the particle, and then here we have the Planck's constant over m times v. And if the velocity, if kinetic energy is doubled, so you have the kinetic energy is initial was equal to 1/2 mv squared. So if the kinetic energy is doubled because of the velocity, that means for velocity you had to have the square root of 2v squared. When you square and you square, you get double as much kinetic energy as before. So for the new wavelength with the new kinetic energy, you would have the expression of the wavelength, de Broglie's wavelength, would be equal to the Planck's constant divided by mass, and you would have the square root of 2 times the velocity. And let's call this one the new one. So the new wavelength is equal to 1 over square root of 2, the old wavelength. And this was your old wavelength, the expression of the old one, the expression for the new one. So that would be our expression. So we can see that the answer is going to be E. In this question, they say that de Broglie's wavelength of a neutron happens to have the same numerical value as the wavelength of the photon. Which of the following is true? And then we have the neutron and photon have the same speed. The neutron and photon have the same energy. The photon does not have the mass. We have to remember that part. The neutron and photon have the same frequency. The neutron and photon have the same momentum, and the neutron and photon have the same mass. I'm going to write de Broglie's wavelength formula before I start thinking about the answer. So the wavelength is equal to the Planck's constant over the momentum. And when I look at this question, because the photon has no mass, I cannot say that they have same speed. So I could rewrite as m times velocity, but the photon has no mass, so I cannot say they have the same velocity because the photon doesn't have mass. So what I can say is that the neutron and photon have the same momentum. They may have different masses, but the mass times velocity, or the momentum of the photon, is equal to the momentum of the neutron. In this question, they say two monochromic beams of light have different frequencies. So let's highlight everything that's given different frequencies. and beam R has twice the frequency of beam S. So beam R has the frequency that is twice the frequency of beam S. And if momentum of the photons in beam R is PR is in momentum in the photons with the beam R, and PS is the momentum of the photons in beam S, which of the following is true? So before I start looking at the answers, I'm just going to solve the problem. So I know from de Broglie's wavelength, I have the Planck's constant divided by the momentum. So if I'm looking at the momentum of PS is going to be equal to h divided by the wavelength. And that's the wavelength of S. And then the wavelength of S is h divided by the speed of light over the frequency of S. So that will give me this expression. Then the momentum of R is going to be Planck's constant, the frequency of R, and over the speed of light. Now I'm going to compare these two. That is my momentum of S. The frequency of R is twice as much as frequency of S. So right here, I have twice as much frequency as the frequency of S. So that means the momentum of R is twice as much as the momentum of S. And that's the answer. The answer would be A. In this question, they say hypothetical atom has an electron energy level diagram as shown. If a gas of these atoms were excited, which of the following photon energies would you expect to be emitted? I redrew these states for you, so I have bigger space to draw the energy levels. So the excited atoms will populate all the levels, and there are two excited states in one ground state. So there will be transitions from, so I can have a transition from, so these will be my excited states. So here is one excited state. Let's choose this color. So here is one excited state, and here is another excited state. So my electron can jump from this excited state to that excited state, or jump straight to the ground, or the electron could jump straight to the ground. So if the electron jumps from 2 electron volts to 5 electron volts excited state, the photon is emitted of 3 electron volts. And in this case, the photon emitted is 7 electron volts. And in this case, the same 7 electron volts. And if electron went this path, let's look at it this way. So if the electron went this path, to get to the ground level, the electron has to jump one more step right here. And then in this case, the electron would emit 4 electron volts. So the only choices where I have 3 electron volts, 4 electron volts, and 7 electron volts is C. And the ionized state is the electron that is becoming free. So it doesn't need any energy to be to leave the atom. So the only excited states that we have to look at are the ones that are 2 and 5 electron volts. Next question is related to the previous question, and they say the photons of a continuous range of energies 2 to 5 electron volts are sent through the gas of these atoms. If the atomic electrons of the gas are distributed over all possible energy level as shown in the graph, if the photons that are coming carrying the energy levels 2 electron volts or greater, so greater than 2 electron volts, or between 2 and 5, it doesn't matter. So that means right here, if an electron is right here, it only needs 2 electron volts. If the electron is right here, it needs 5 electron volts. So if only 5 electron volts would eject this electron or ionize this electron, the lower energy will not. But if the electron is at 2 electron volts, any amount of energy greater than 2 will ionize this electron. So the answer for this question would be all of the energies can be absorbed, because anything greater than 2 can be absorbed, because the -2 electron volt level can absorb anything from 2 and higher. It only needs 2 electron volts to be ejected and will be ionized, and then the rest of the energy can be the kinetic energy. In this question, they say ultraviolet light with a frequency of 310 to the 5th hertz strikes a metal surface and ejects electrons that have maximum kinetic energy of 6 electron volts. What is the work function in electron volts of the metal? We start with the energy of the photon, which is the Planck's constant times the frequency of those photons, and that will be equal to the work function plus the kinetic energy that is left for the electrons to have. They're asking me to find the work function, so this is the part I'm looking for. So the work function is going to be equal to the energy of the photons. So they give me the kinetic energy of the electron in electron volts, so I'm going to plug in my my Planck's constant in electron volts, which is 414 10 to the -15, and then the frequency is given 3 10 to the 15, and then minus, so I have to subtract my kinetic energy from the energy of the photons, so it's going to be minus the energy of the photons, which is kinetic energy of the electrons, which is 6.1 electron volts. So I get the work function is equal to 6.32 electron volts. For the next question, they say that an FM radio station broadcasts at the frequency of 98.1 10 to the 6 hertz. The power radiated from the antenna is 5 10 to the 4th watts. How many photons per second does the antenna emit? So if they give you the power, so the power is equal to how much work happens in a second per time. So that one is 5 10 to the 4th. So that means it produces the work of 5 10 to the, it's in watts, 5 10 to the 4th joules each second. So it's joules per second. I don't have to write this per second, but I'm just going to remember that this would happen per second. And they ask you how many photons does it emit per second. So this is the energy of those photons. So I have the energy of the photons is h times the frequency, and that is equal to, from the numbers that are given, I have 663 10 to the -31st, 34th, I always make the same mistake, times the frequency, which is 98.1 10 to the 6. So the energy of the broadcast frequency of the emitted radiation is equal to 6.5, so this is going to be 6.5 10 to the -26 joules. So this is the energy of one photon. So this would be the energy of one photon, and this is the energy of all photons. So if I divide this number by the energy of one photon, I'm getting the number how many photons there are. So the number of the photons is the energy of all photons divided by the energy of one photon. And this will give me 7.7 10 to the 29 photons. In this question, they say ultraviolet light is responsible for sun tanning. Find the wavelength of an ultraviolet photon whose energy is given. So if the energy of the photon is given, so the energy of the photon is 6.4 10 to the negative 19, and that is equal to the Planck's constant times the frequency. And they ask me to find the wavelength, so I'm going to replace the frequency with the wavelength, so that's c over the wavelength. So I have the wavelength is equal to speed of light times the Planck's constant divided by the energy. Now I'm going to plug in the numbers, and I have 310 to the 8. Planck's constant, the energy is given in joules, so I'm going to plug in Planck's constant in joules, 663, 10 to the negative 34. I'm not going to make that mistake here. And then divide by the energy that is given, which is 6.4, 10 to the negative 19. So the wavelength of ultraviolet light is equal to 311 nanometers, and nano means 10 to the negative 9. In this question, they say a light source emits a beam of photons. Each photon has a momentum 2.3 10 to the negative 29 kilogram meters per second. What is the frequency of the photon, and to what region of the electromagnetic spectrum do the photons belong? So if they give you the momentum, I can use de Broglie's formula, which is the wavelength is equal to the Planck's constant over the momentum. So from here, I can see that if I need to find the frequency, that's going to be the speed of light over the frequency equals to the Planck's constant over the momentum, and then the frequency is going to be equal to speed of light momentum over the Planck's constant. And since everything is not given, well, there's no electron volts involved right now, my Planck's constant is going to be plugged in joules times seconds. So I have 310 to the 8, and momentum is 2.310 to the negative 29, and divided all by the Planck's constant, which is 663, 10 to the negative 34. So the frequency is equal to 110 to the 13 hertz. And if I look at the spectrum of electromagnetic radiation, so here is my the spectrum of electromagnetic radiation, and I see that 10 to the power of 13 falls somewhere around the infrared frequencies. In this question, a photon of real light and the wavelength is given 720 10 to the negative 9 meters, and ping pong ball mass of 2.2 10 to the negative 3 kilogram have the same momentum. So what is the speed of the ball when it is moving, so it has the same momentum as the photon? So the de Broglie's wavelength formula, we have the Planck's constant divided by the momentum. So the momentum is going to be equal to the Planck's constant over the wavelength. And since this momentum of the photon is equal to the momentum of the ball, I have the mass times the velocity of the ball, and I have to find the velocity of the ball. So the velocity of the ball is going to be equal to, if I look at this part, is equal to the Planck's constant divided by the wavelength of the photon times the mass of the ball. So I have 663, 10 to the negative 34th, divide that by the wavelength, which is given 720, 10 to the negative 9, and the mass of the ball is 2.2, 10 to the negative 3. So the velocity of the ball is equal to 4.2, 10 to the negative 25 meters per second. In this question, they say, suppose the maximum speed of 1.2 kilogram mass attached to a spring with a force constant K of 35 newtons per meter, and has a maximum speed 0.95 meters per second. They want you to find the frequency of oscillation and the total energy of this mass spring system, and then determine the size of one quantum of energy in this system. So if you have the frequency formula for the spring, so that is going to be 1 over the period, and the period for the oscillations is 2 pi, and the square root of m over k. So if you simplify this, you have the square root of, or 1 over 2 pi, and the square root of k over m. So if I plug in my numbers, I have the frequency of this oscillation is 1 over 2 pi, and then I have the k, which is given 35, and the mass is given 1.2. So that will give me 0.86 hertz. And then if I want to calculate the maximum energy of the system, I can do kinetic energy of the system, which is 1/2 mv squared. I don't know the compression of the spring, so I cannot do potential energy. And that is equal to 1/2. The mass is 1.2, and the velocity is 0.95 squared. So that gives me 0.54 joules. And then they say, so that was supposed to be hertz. And then they say that we determine the size of one quantum of energy of this system. So if this energy is replaced with h times f, so you would have the Planck's constant times f, then you would have 663 10 to the negative 34th times the frequency of this oscillation, 0.86, and that would give you 5.7 10 to the negative 34th joules. So this would be the energy of one quantum during this oscillation. In this question, they say energy level diagram of a theoretical atom is shown. If a gas of these atoms is excited and then allowed to fall back to the ground level, which of the following photon energies will be never emitted? I'm going to check each energy to see if it's possible. So 1.2 electron volts. If I go from 0.6 to 1.8, the photon energy is going to be emitted, the difference between those two, and it's going to be 1.2. And then if I look at 6.5, so I need to look at the difference between these energies levels, and I don't see, only if the ground level, not the ground level, if ionized level, if you jump from ionized level to 6.5, you could emit 6.5, but the electron is at the excited atom levels, and ionized level is the when electron is becoming free. So 6.5 wouldn't be one of the choices. And then for so that could be your answer. So let's look at the other ones. 2.5. If you electron jumped from 4 to 6.5, the energy level that would be emitted is 2.5, so that is possible. And then for 9, if the electron jumped from 1.8 to 10.8, the energy level that could be emitted, the photon, would be 9, so that is possible. So the only one that is not possible is 6.5, because the electron wouldn't be on one of the excited levels of the atom. It would be already ionized electron. I found this question in one of the finals for universities. So a hydrogen atom is excited from a state with N1 to the state of N4. Based on Bohr's hydrogen model, consider the following. So the first question is, calculate the energy that must be observed by the atom for this transition. So at first I have to calculate the energy levels. So I know that E1 for the hydrogen level is equal to negative 13.6 electron volts. And then if you wanted to calculate the nth level, the formula would look like negative 13.6, and then you have the number of the protons in the atom. In this case, it's hydrogen atom, so it's 1, and then the level at which the electron is going to be jumping. So for the hydrogen atom, this would be the formula. So if I'm calculating the energy level at the 4th level, then I have negative 13.6, and then I have 1 over 4 to the 4 squared. So that will give me negative 0.85 electron volts. So now I'm gonna draw the energy levels, and it usually looks something like this. And here is gonna be the ground. So 1, 2, 0, or let's say 1, 1, 2, 3, 4, 5. I need level 4. So on level 4, the energy level is going to be negative 0.85 electron volts. And level 1, the energy is negative 13.6 electron volts. So if the electron would jump from level 4 to the ground level, level 1, then the energy that is emitted is the change of the energy between two levels, and that would be negative 0.85 minus negative 13.6, and that will give me the energy level of 12.75 electron volts. So right here you would have a photon energy emitted of so the energy of the photon emitted would be equal this much. And if they ask me what would be the frequency of that photon, then I would set it equals to the energy of the photon, and I could calculate the frequency of that photon would be the energy level change, which is 1275, divided by Planck's constant h. And in this case, because everything is in electron volts, I would divide by 14, 10 to the negative 15. And I would get the frequency of that photon, 302, 10 to the 15 hertz. So that would be the frequency of this photon. And in this part of the question, they ask, calculate and display on an energy level diagram all the different photon energies that may be emitted from the excited atom. And hint, there are 6 different optical transitions straight from the excited state and going down toward the ground state. Each emits a photon of a particular energy level. So I'm going to show you the possibilities of that could happen. So from the 4th level, you could go jump to this level, you could jump to this level, you could jump to that level. Then from let's say from the 3rd level, the jump could be this one, and the jump could be that one. And I don't have to look at the jump between 3 and 2 for the green line because it's already accounted for the last one in yellow. So these are the ground, the energy levels. And then for the last one, you could jump from this level to that level. And I already pre-calculated for you all the energy levels because I'm running out of time, only 1 minute left. And so what you have to do next is to subtract the energy levels that are possible when the electron is jumping from one level to another. I'm going to do for one of them. The jump between the 4th and the 3rd one would be the difference between 0.85 and 151. That gives me 0.66 electron volts. The jump between 4th and the 2nd level, you would have to subtract 0.85 and 3.4, and that would give you 2.55 electron volts. And the jump for the 4th and the 1st level, we already did it in the previous part, that was 1275 electron volts. And I'm going to write the answers for you quickly for the other two. Here I wrote the energy levels for jumping between the 3rd and the 1st and the 3rd and the 2nd, and the second and the first levels. You can pause quickly and go over these calculations if you want to check the work. It's like repetitive, and otherwise, thank you for watching this video, and I will see you in the next one.